So, hello everyone. In this presentation, I will speak about the role of aluminum and lithium on the formation and structure of synthetic XR product. I will talk about research background and synthesis of XR product and the role of aluminum and lithium on the formation and structure of XR product, and followed by a short summary. In terms of SMS in mitigating alkali-silica reaction, there are quite a lot of study has been conducted in this area. We have mechanisms, for instance, reduction of pore solution alkalinity, or increase of alkali binding, consumption of Portlandite, and reduction of permeability. With respect to aluminum-rich SMS, we have some specific assumptions related to the mitigation of XR. For instance, incorporation of aluminum increases alkali fixation capacity of CSH. In fact, this is not the case, as it will not increase the alkali fixation, and also limited dissolution of amorphous silica in presence of aluminum, or initial formation of aluminum silicate or later precipitation of zeolite. Also, sorption of aluminum on XR product. In fact, this could be because of the contamination of the product during the sample preparation. And then we have lithium salt in mitigating XR. This is a bit more complicated. First of all, we have a different type of lithium salt, and second, because lithium is invisible from semi-DX, much less information can be valuable for us to understanding the mechanism of lithium in mitigating XR. Two basic mechanisms proposed in literature. One is formation of lithium silica complex creates a physical barrier preventing further XR. And second is the mitigating formation of XR products. The research challenges, when you look at the reaction product from the concrete, that you see the size of the reaction product is actually very small. And with a certain expansion where correctly is observed already, and we have only 0.02 gram per cubic centimeter of your concrete, then you have a sense of the amount of XR product, which is very little and cannot be analyzed with the conventional laboratory techniques. So with that, we came up with the idea that we're probably able to synthesize XR product in large amount, and then we can compare that with those formed in concrete. This is very important because most papers, they also synthesize the XR product, but few studies have compared with that formed in concrete. Now we have advanced techniques, for instance, Raman macro spectroscopy or synchrotron microexcited or capillary excited can be used to analyze the product formed in concrete. With this fingerprint information, we can verify the product we have synthesized is identical to those from the concrete. After successfully synthesis of the XR product, we can develop thermodynamic data relevant to the XR product from the concrete. And with the characterization of the synthetic XR product, we can also unveil the crystal structure of the XR product. For instance, here we have different types of crystalline XR product formed at different temperatures. And the main focus of this presentation will be the 13.1A and the 10.8A. This is the basal spacing of the crystalline XR product. We know it now is potassium silica white, a natural mineral observed in geo and sediment. It has an identical structure with the XR product at accelerated conditions. So then we can predict the formation conditions of XR product. We can also predict the mitigation conditions of XR, the focus of this presentation. And there you can say in terms of starting calcium to silicon ratio, where you have formation of either crystalline XR product or amorphous one or CSH, and this mirrors quite well with the distribution of the different types of XR product in the concrete vein. As I said, that the synthesized XR product must be identical to those formed in concrete. Here we use the micro-Raman spectroscopy method. Here we'll not go into detail about different wave numbers, what that mean. But what you need to say here is the synthetic product is identical to the XR product formed in concrete, or independent whether it's in cracks or in air voids. Okay, and lower temperature, more relevant to filled concrete, the synthetic product is comparable with what we have seen in concrete. With that, we have the chance to look into the mitigation mechanisms. Here I looked at samples with initial alumina to silica ratio from 0 to 0.3, and we look into two different temperatures. And the first result of XRD and alumina methanamide, when you don't have alumina in the samples, you have a pure XR product, 10.8 XR product at lower temperature. But with the increase in the alumina to silica ratio, then we have an increased amount of gibbsite, which is indicated by these diffractions. However, the peak related to 10.8 XR product, only the intensity is reduced caused by simply a dilution effect. This is also confirmed by alumina methanamide, where you can see the increased amount of gibbsite. There's no secondary alumina-rich product. And then we look into the chemical compositions with semi-EDX. Here is XR product. Here is the XR product mixed with gibbsite. Most of the XR product region do not contain aluminum. There's one closer to the gibbsite, has some aluminum. This is just like a physical mixture of the two phases, which indicate that aluminum is not sorbed on the XR product. And we also can model the formation conditions of XR in presence of aluminum, where you can see there's no change of the aqueous concentration with the increasing alumina to silica ratio, which is more or less consistent with what we have seen from experimental results. Here you can also see we have formation of CSH, 10.8 XR product, at the increased amount of gibbsite. Confirm that the formation of XR product is not affected. Of course, here during the modeling, we have prohibited the formation of zeolite. It just takes a long time. From the kinetics point of view, we have prevent its formation. And then at high temperature, without aluminum, we have formation of potassium silicate. We have some trace of XRP1 product, which has a nanocrystalline structure reported earlier. But here is just the minor. We don't focus too much on this in this presentation. And then with the increase in the alumina to silica ratio, still we can see potassium silicate for this sample, but the amount is substantially reduced at alumina to silica ratio 0.3. At the same time, you have formation of alumina silicate. Formation of this phase can be confirmed by alumina methanamide. Here we have more gibbsite and high alumina to silica ratio. The amount of gibbsite is reduced because of formation of more zeolite precursor. Okay, and we also look at the morphologies. Potassium silicate has this needle-like structure, and zeolite precursor have this sponge-like morphology. And then we also do the thermodynamic modeling, and there we also compare the aqueous concentration with the measured concentration. You can see the calcium and aluminum, silicon and potassium follow the same trend between experiment and calculation. With increasing the alumina to silica ratio, the amount of potassium silicate is reduced with the formation of zeolite. And the last part is lithium salt in mitigating XR. Here we look at lithium hydroxide, and the reason to use lithium hydroxide is try to reduce introduction of foreign ions which may affect reactions. Here I have increased the lithium to silica ratio from 0 to 0.5. You can say from the XRD, with the increase in the lithium to silica ratio, the formation of crystalline XR product is prohibited. And then we have a formation of amorphous product within this range, and at higher lithium to silica ratio. In addition to this phase, we have also a crystalline phase which is related to lithium silicate. But the amorphous phase here is very similar to the XRP1 as I mentioned earlier. And the highest lithium to silica ratio for these samples in the absence of potassium. then you can see amorphous product here, and with some CSH, and from silicon NMR. And in the case of formation of AXR-P1 and the AXR product is depolymerized, okay, with the increase in the lithium to silica ratio is further depolymerized. Here you have already some species related to lithium silicate. For the one in absence of potassium and highest lithium, where you can see a very complicated NMR spectrum. And this contains some CSH, as you can see from XRD, and it contains a lot of Q3 species, which is similar to the potassium XR product. And then the question is, if this is a lithium XR product, whether this will cause any expansions. To summarize, at lower temperature, aluminum does not prevent formation of XR product. XR mitigation mechanism is most likely related to slow down the dissolution rate of reactive silica as proposed in literature. So at high temperature and high aluminum concentration, formation of XR product can be prohibited due to formation of zeolite precursor. So in presence of lithium, formation of crystalline XR product can be prevented, while formation of an amorphous product or crystalline lithium silicate is observed. So the hypothesis of proposed earlier studies on formation of physical barrier due to the precipitation of lithium-containing reaction product is not necessarily the mechanism for lithium in mitigating XR, because in this case, if there's a barrier, then we should be able to see some unreactive silica, but which is not the case in our experiment. So finally, I would like to thank you for your attention.